Hello, and welcome to Hacking the Colony, our research on disinformation in Stigmergic networks. I'm Antonio Lopez, and I'll be joined by my co-author Asha Iswali later in the presentation. Stigmergy is an environment-mediated communication modality that enables large-scale coordination in societies of insects. You can think of it as hikers leaving trail markers for others. Ants use it for foraging, nest building, and even to protect themselves from predators. As such, there's a lot of interest in robotics to take inspiration from Stigmergy. For example, you can explicitly simulate pheromone-based communication, as pictured here, or imagine applying these concepts in construction. However, Stigmergy is fragile. Here you can see an example of ant milling, or a death spiral, where ants get separated from the main foraging party and begin to follow each other to the point of exhaustion. This can happen naturally without any outside interference. Some organisms have even evolved to exploit this mechanism, such as parasitoid flies eavesdropping on alarm pheromones, or orchids producing pheromones to trick bees into pollinating for them. We set out to explore how can we attack Stigmergy using existing or limited tools, and likewise, how can we defend against attacks using those same tools. There's no perfect way to simulate exactly what ants do, but we can make some approximations to qualitatively show their behavior. Let me explain how we built our model. In our model, ant position is continuous, while pheromone is deposited in discrete cells. Imagine walking across a tiled floor. Ants leave a trail of pheromone whose intensity changes over time. When an ant passes over a grid cell, it deposits pheromone if the intensity is greater than the cell's level. Note that the plus sign here is a max operation, not a sum. After a period of forward motion, an ant reorients itself. It sends out 32 probing vectors, scouting out potential destinations. Those vectors have random angles and random magnitudes within a certain range. The ant picks the cell with the highest concentration of its target pheromone and adjusts its angle accordingly with a little random noise. Note that it's possible that a cell within range, for example X, has a higher concentration than the one the ant picked. Here it picked O. It just so happened that none of the probing vectors landed on X, so it was never evaluated. Finally, here we can see a typical foraging task. Ants set out to follow food pheromone, leaving behind a home pheromone. Food pheromone doesn't exist at first, so they move randomly. But once an ant finds food, it flips its operation, leaving behind green food pheromone and following blue home pheromone. Once a path to food is found, ants form a sort of pheromone highway, easily following trails in each direction.
Thank you, Tony. Now that we have seen how the cooperators behave, let's see how can we attack the colony using minimal cognitive capabilities. For that, we will be using one of the basic properties of Stigmergy, which is whoever is reading the information doesn't really care about who has written it. We introduced a small fraction of the colony as the detractor ants. These ants lay down a trail of fake food pheromone. This trail is indistinguishable from the trail of actual food pheromone for both the detractor ants and the cooperator ants. Hence, now the detractors can distract the cooperators from finding the actual food. In addition to laying down this fake trail, the detractors also chase what they think of as the food pheromone. And that's why we can see that the detractors stay in a very small cluster because they keep following each other's trails. Understanding this effect, we introduce an improvement. Now, the detractors have an oracular knowledge of where the food is, so they only attack in that particular direction. In addition to that, the attack is also delayed slightly, forming this wall-like structure. This wall has an interesting feature. The ants with food in their hands can easily find their way through it to deliver food at the nest, but they get lost while trying to get back to the food. But there was still a catch. As time passes, the intensity of the fake trail laid down by the detractors, it continues to decrease. And it just cannot keep up with the fresh trail of the actual food pheromone being laid down by the cooperators. And that's why we can see that the attack quickly breaks down, and at the end of it, the detractors are rendered harmless. To deal with that issue, we introduce the final improvement. With that, If a detractor visits the nest, it can again start secreting the fake food pheromone with the highest intensity. We introduced this improvement with an imagination of detractors stealing some energy from the nest. Now, if such a detractor with much fresher intensity joins the wall back again, all the ants in the wall might think that this new ant has much higher food pheromone intensity than what we have here. So that direction must have food. And hence, all the ants in the wall eventually migrate back to the nest. But again, at the nest, the detractors keep refreshing their fake food pheromone intensity to the maximum by constantly visiting the nest. Hence, the detractors lay down a highly efficient trap at the nest. The effectiveness of this trap is to such an extent that we can see at the end, no cooperator is out there exploring and almost all the ants are trapped at the nest. To evaluate the performance of the attacks, let's analyze these heat maps. We have plotted these heat maps for percentage of detractors in the colony versus evaporation rate for the fake food pheromone. More to the right you go, more detractors you will have in the colony, and higher up you go, lesser will be the evaporation rate for the fake food pheromone. You can see the heat maps for fraction of cooperators that collected food and fraction of cooperators that delivered food, and food bits per cooperator collected and food bits per cooperator delivered. If a particular configuration is red in color, that means that configuration is beneficial for detractors, and if a configuration is blue, that means it was beneficial for a cooperator. One of the first observations to be made here is that there exists a boundary between the reds and the blues, which means that beyond this boundary, the detractors will tend to dominate. Then we also see that the heat maps for food collection and the food delivery are almost identical, which means that if an ant is able to find food, it will most certainly deliver it back to the nest. Then finally, when we analyze the data, we can see that when we have a mere 0.39% of the colony as detractors, they are still able to drop down the food collection performance by more than half. It drops down from more than 20 to less than 10. And that really tells us Stigmergy is fragile. And after seeing how can we attack the colony, now let's see how the colony can defend itself with the same assumption of no extra cognitive capabilities. For the defense, we introduced a third type of pheromone, cautionary pheromone. When the ants are looking for food, they will also lay down this cautionary pheromone in addition to the normal pheromone secretion explained earlier. The cooperators therefore will lay down two types of pheromones. We also introduced the concept of patience. If an ant is following a food trail without finding food, then its patience will continue to decrease. And as the patience decreases, its cautionary pheromone intensity will increase. These two concepts help in choosing the next direction for the movement. As Tony has explained earlier, the ants send out certain number of probing vectors. But in this case, if a probing vector ends in a grid cell where we have more cautionary pheromone than the food pheromone, that grid cell will not be chosen. That's why we see that the grid cells X and O were not chosen, but the grid cell P, which has more food pheromone than the cautionary pheromone, is chosen for the next movement. With such a simple defense mechanism, let's see how the colony holds up against the attack. The attack starts just as usual. When most of the ants are trapped, their patience decreases and cautionary pheromone intensity will slowly increase. We can start to see the cautionary pheromone yellow in color. Notice how the cautionary pheromone is concentrated at the nest where attack is going on and not somewhere else. The ants can now finally find their way out of the trap and find the actual food trail. Eventually, the ants find a solid trail to the food and back. But also notice that not all the colony get to become the part of that trail, because some part of the colony will still be needed to keep the cautionary pheromone competing against an ongoing attack. To evaluate the performance of defense, we will be studying how long a cooperator should take to calm down after running out of patience. We will also be looking at what should be the maximum patience for a cooperator. For the reference case alpha, we can see that if we set either of these two parameters to extremes, the defense is not that great. And that is because the ants are too cautious of even the good trails. But if we set both of these two to just about right, then the colony is able to collect more than 8 food bits per cooperator. This number used to be 0.12 without the defense. Hence, we can say that the cooperator could successfully defeat the attack from the detractors.
Thanks, Ashe. To sum up, we introduced a method to disrupt a colony's foraging task, leaving fake food pheromone. We found that as few as 3% detractors can catastrophically reduce food collection. We implemented a countermeasure, cautionary pheromone, which masks suspicious food pheromone. This measure works well, but it's not a magic bullet. There are a few ways in which we can further explore attacks on a network and countermeasures. In nature, ants can learn to ignore but not avoid pheromone trails. Robots have no such limitation. They could learn that certain areas are bad and move away from them. We could also supplement pheromone with some other signals, such as observing behavior of neighboring ants. That concludes our presentation. Thank you so much for your time and interest.